Okay, students, let's get through this lecture. Well, I thought I had the right. Oh, I made a boo-boo. There we go. Now, it's more like it. So let's look at rotational motion for a little bit, describing and circular and rotational motion. Of course, hopefully all of you know what we mean by rotational motion. I mean, come on, it's someone that's rotating. It's rotating about an axis, okay? Now, in order to describe it, we have to use a little bit different terminology than we use when we are looking at linear motion. We use what is called the angular position. The angular position is the arc length. It is the arc length, okay, or the ratio of the arc length to the radius, okay, of where the particle is actually located, all right? And notice too that we move counterclockwise. It's very important that you understand that we measure arc length counterclockwise. So that is positive, going this way would be negative, okay? All right, so this is positive, negative, okay? All right, now, so we measure that in radians. Now, we call that an angular unit, but what the heck is a radian, okay? Do you have radian rulers? Do you find a radian measuring tape? I've never seen one. I'm saying they don't exist, but I'm pretty sure they don't, okay? And the reason they don't is because we determine everything in units of length or in degrees or both, okay? So even though we call that an angular unit, it's kind of in a way unitless, okay? Like pi, okay? Well, what is pi? Well, we know what the constant is, but what is the unit? Well, it's pi, okay? All right, now, so here's how we calculate the arc length in radians. We take the arc, or the angle, the angular movement in radians. We take the arc length divided by the radius, and that gives us the angle in radians, not degrees, okay? Of course, we can turn around and find the arc length by multiplying the radius times the angle, okay? In radians, all right? Not in degrees, in radians. So when we look at revolutions, and of course, what is a revolution? Well, like you've got an object moving in a circle here, like a bicycle wheel, okay, or the spokes of a tire. All right, you have an object moving in circular motion, okay. If you think about it, when you make one complete revolution, notice that is 360 degrees, okay, which is the same as saying 2 pi radians, okay? 2 pi radians, all right? Okay, so remember that. So this is in radians and that's in degrees. All right, so linear motion, we talk about how, objects with greater displacement have greater velocity. Well, for uniform circular motion, a particle will undergo a greater angular displacement. I mean, come on, y'all, that's common sense. So if you have an object that moves this far and then one that moves that far, or let's say we got an object that moves from here to here and then one that moves from here to here, well, this one, needless to say, if it's in the same time interval, which it should be if it's uniform, then it's going to have a greater angular velocity. So again, angular velocity is the angular displacement that an object moves, or a particle moves, every second, okay? Here's another formula to put on your formula sheet, okay? So angular displacement, okay? So this is angular velocity. Now, I know some of you are saying, well, now, wait a minute. We said that was, omega was angular frequency. Well, if we're looking at the amount of arc displacement given a time interval, then it's angular velocity. If we're looking at the number of cycles, then it's angular frequency. Okay. All right, and we'll look at that a little bit here in a little bit. Okay. So again, there's another formula to put on your formula card. All right. Now here they give an example for uniform circular motion. We can say angular displacement is the change in theta as long as we use a corresponding time interval. For each particle, choose the angular displacement corresponding to the motion from time 1 to time 5 seconds. Okay, so from here 1 to 5, it's what? Pi over 2, isn't it? Yeah. So it's pi over 2 radians in 5 seconds, and there's your answer. Okay, 0.314. The next one, however, goes from here to here, which is pi. Notice it has a much greater angular velocity, 0.62 radians per second. Okay. All right, so it's has a greater velocity because it covered a greater arc length. Okay. All right, now angular displacement, how do we find it? Same way we found linear displacement. Theta final minus theta initial is equal to the change in theta, which can also be found if we know the angular velocity and the time. Then we can multiply those two together and find the actual angular displacement. Okay, so there's another equation for your formula card. So angular speed, of course, is the absolute value of the angular velocity. Now notice there's a difference in angular speed and angular velocity, so we take the absolute value, okay? And of course it is related to the period. Notice this right here, that is frequency, y'all. Okay, 2 pi over t is frequency. So angular speed is 2 pi over t, or 2 pi f. And so we can find the angular speed by using that equation there. Okay, now a ball rolls around a circular track with an angular velocity of 4 pi radians per second. What is its period of motion? Well, it's pretty obvious, 1 over 2, because when you divide, when you put 2 over, when you put 2 over, well, shoot, 2 over 4, yeah, you get 1/2. Okay. All right. Or you can write it that way. You can write it that way too. But with that value, it would have been half. Okay. All right. Speed and angular speed, there is a difference. When we're looking at just the speed, okay, the linear speed, when we want to use angular speed and find the linear speed, then we do what? We multiply omega times the radius, okay? And of course, that has to be in radians per second, okay? You got radians per second times a meter, and you get meters per second, okay? All right? So please keep up, and by the way, please keep up with the units. Here, of course, that is in radians, okay? And of course here, I think this would be in radians per second, and it tells you that, does it not? Okay, well, all right, there's your units. So be sure you keep up with the units, okay? But this here would be meters per second, because that is radians per second times a meter gives you meters per second, okay? All right. Rotation of a rigid body, okay? Now, what do we mean by a rigid body? Well, like a wheel, a bicycle tire, something like that. A bar that's rotating about a central axis. You have 3 kinds of motion. You have translational, which is moving in a linear fashion. You have rotational, which is spinning about an axis. And then you have a combination of both, rotational and translational, okay? So please understand there are different kinds of motion, and you can't even combine motions, all right? All right, now please pay close attention to these next few slides. Now when we look at a rotating body, every point along this rotating body, doesn't matter where it is going to have the same angular velocity. You say, well, now how in the world is that? Now I didn't say linear, I said angular. You say, well, how can that be? Well, because the amount of arc distance is the same, okay? Now, if the arc distance was different, then, you would have a different speed. but the arc distance is the same, okay? They have the same angular velocity, okay? All right. All right. Okay. Okay. All right. All right, now, Rashid and Sophia are riding a merry-go-round that is spinning steadily. Sophia is twice as far from the axis as Rashid. What is her angular velocity? Okay. It's the same because the arc distance is the same. Okay. They on them over spinning steadily. Sophia is twice as far from the axis as Rashid. Sophia's speed is what? Okay, so Sophia is twice as far as Rashid. So twice as far. So what's it going to be? Well, it's going to be related to whatever the angular speed is times the radius. So please do not confuse speed and angular speed. Okay, notice the situations were the same, but we got two different answers. Okay, we got two different answers. So please listen. Linear speed is different than angular speed. The speed of this object here is going to be slower going that, well, oops, I drew the arrows the wrong way. The speed of that object here, that point there, moving in that direction, is going to be slower than it is here. Think about the rotation of the Earth. Okay? See, the rotation of the Earth, it has the same angular speed, but when you look at it linearly speaking, when you look at places like, you know, a point on the globe, you look at the equator is moving faster than anybody else on the Earth. Why? Because it has the greatest radius, the Earth does at that point. Okay? All right, now angular acceleration, well, is the same as linear acceleration. It's just, instead of using linear, we use an angular velocity, okay? So anytime you change angular velocity during the time interval, you have angular acceleration. So please put that on your cheat sheet, on your formula card. There are the units. Of course, it's radians per second squared. Okay? All right, now this is very important to remember. If you want to write this on your formula card, you can, or just make yourself a note. How do we know if it's positive or negative? Okay, if the rigid body is spinning counterclockwise and speeding up, then it has positive angular acceleration, or if it's rotating clockwise and slowing down, then it has positive angular acceleration. Okay? When is it negative? If it's rotating counterclockwise and slowing down, or rotating clockwise and speeding up. Okay? So here's when it is negative, here's when it is positive. Okay? All right. Now, all right, fan blades slowing down. What are the signs of omega and alpha, angular speed and angular acceleration? Well, it's slowing down, so therefore omega is negative, but alpha is positive. Angular acceleration is positive, okay? All right. All right. Fan speeding up. Notice the direction it's moving. What are omega and alpha? Well, they're both negative, okay, because it's going clockwise and it's speeding up. Okay, here are some comparisons of equations to linear velocity and circular motion, or linear motion and circular motion. And you can see how these equations relate to each other, okay? Notice how the constant acceleration equation is the same. You just change it to change in angular displacement, angular velocity, and angular acceleration. Okay? All right. So might be wise to put those on your formula card. You can put these on there. Okay? You should already have them on there. Okay? All right, tangential acceleration is a component of acceleration which is going to be tangent to the circle, okay? So when you look at tangential acceleration, well, here's centripetal acceleration. Tangential acceleration should be in the same direction as your velocity component, okay? And that when you have, this is for uniform circular motion, but when you look at non-uniform circular motion, okay, well, it's still going to be tangent, still going to be in the same direction as your velocity vector, okay? So your tangential acceleration is in the same direction as your velocity, okay? That's the best way to remember tangential from centripetal, okay? Tangential's out here at a point, it's tangent at the point, okay? Centripetal is center seeking, all right? That's the best way to remember it. So how can we find, relate tangential acceleration to the angular acceleration? Well, we use this equation right here. Remember, now you say, well, why are we using that? Because that's for linear velocity. Yes, it is. Well, we substitute in right here, and so the change in omega r, change in omega times r over t, okay, we get what? The change in angular velocity times the radius divided by the time, okay? And this right here is angular acceleration, so we can just write it that way. So if you want to, you know, it all depends on which way you want to remember it. You know, this is how we found linear velocity. And remember what I said, it's in the same direction as the velocity. In other words, it's in a linear direction, not a circular direction. Okay, it's not based on the amount of arc. Okay. All right, now torque. Torque is is a force that has a tendency to cause rotation or stop rotation. Okay, that's the best way to remember how torque works. We use forces and a lever arm to cause things to move. You see here the picture of the door and the hinge. Well, that operates on a lever, wheel and axle principle, okay? You have the door as acting as a lever, spinning about a very small axis, okay, which more than likely has a pin going through it. All right, that's an axle. And so looking at this diagram, we want to rotate this thing. Which one would have the greatest chance of causing it to move? If we were going to try to move this door, well, do I want to apply my force close to the hinge? Do I want to push on the end of the door? Do I want to pull on the end of the door that way? Or do I just want to push out here as far out on the edge of the door as I can get and apply a force? Which one do you think is going to be the easiest? Well, folks, how do we open doors? We don't push over here close to the hinge. Are you kidding me? We don't push that way. We don't pull. We push as far out in the door at the handle. Okay, that's why the handle is located where it is. We push there. Have you ever noticed these doors with panic bars? You know, if you try to open the door by pushing in the center of the door, it's a whole lot harder, isn't it? So what do? You hit the panic bar out close to the edge of the door, okay, on the jam side, all right? So we define torque, or calculate torque, by looking at the amount of force applied and by the way, the force is perpendicular. To get maximum torque, we want it perpendicular. And then, of course, we can throw in a little trig here in a minute, and we will. What if it's not applied perpendicular? Well, then it'll be the sine of the angle, okay? All right, now, and of course, that's from the pivot point. So how do we calculate torque? Here's another equation. Torque is equal to the radius times the force applied, or MA. We could put MA there, okay? And there are the units. It's a Newton meter. Now, I know some of you are saying, well, wait a minute. I remember studying work in high school physics, and work, a Newton meter is a joule. Well, okay. But we're not, remember now, we're applying a force that causes motion, okay? So we're going to use Newton meters, okay? Newton meters. All right. Now, how do we find the radial line? You hear as you read through the text, it talks about the radial line. The radial line is is a straight line point from the pivot point, the center of the axis, to the point at which the force is applied, okay? Now, you extend that line on out, and based on this diagram, it has to become then the sine of phi, the sine of the angle, because notice it's not applied at a 90-degree angle. An application to get maximum torque would be the best way to apply the force there, not at an angle like that, okay? And again, and this is just more showing you how to determine it. So how would I find my force? Well, it's opposite over hypotenuse. The force is applied this way, opposite's right there, because we want it to move this way, don't we? In a counterclockwise positive torque fashion. So it has to be the sine of that angle. Well, all right. So therefore, we have to take into consideration what we call the moment arm. And the moment arm is this right here. And you say, well, yeah, but I'm not pushing it there. I'm pushing it up here. Well, that's true, but the moment arm is the line that makes a perpendicular or a right angle with the line of action, okay? Notice that's a right angle. Well, again, look at my angle. There's phi. We could label it theta, but for whatever reason I use phi. Okay, it doesn't matter. So notice that phi is what? Opposite over hypotenuse. Okay? So that's what? That's the sine of phi, isn't it? It sure is. Okay? And so our moment arm can be defined that way. All right? Now, so the equivalent expression for torque, as we've already talked about, is the radius of the moment arm times the force. But now wait a minute, how do we measure that right there? How do we find the moment arm? Because we're pushing up here, all we know is this distance from the pivot point to the point at which we apply the force, okay? All right, well, how do we find that line? How do we find that? How do we find this when all we know is this and the force applied? Well, we use sine, y'all, what I just said a minute ago. All right, so if we come in right here, and since the moment arm is here, we substitute in sine theta, and that'll give us torque, okay? So if the torque, now you say, well, when do I use these? Well, look, y'all, if the force is applied at a 90-degree angle, look, that's 90 degrees right there. Okay, the sine of 90 is 1. I don't need sine. But if it's applied at an angle, I've got to have sine, okay? Like this one is, all right? So you might need to remember that. It wouldn't hurt to put that on your formula card. We already have this one. It's just written kind of backwards. They're talking about the torque, the radius of the moment arm. That's what that is, okay? So if the force is applied at an angle, this is at an angle, then we use that equation there, sine of phi, okay? All right, now, and we've already been over this. Which one's going to be the most effective? Well, I hope and pray you say F1. And of course you do. Why? Because it's at a 90-degree angle, and we're using as much of the radius of the door as we possibly can, okay? Now, torque, again, is that force that tends to rotate an object in a counterclockwise direction, and of course that's positive, okay? While a torque that rotates clockwise is negative. Now, you do need to remember that, okay? That's some of that conceptual stuff. So if I'm pushing this way, it's positive. If I'm pushing, okay. If I'm pulling it this way, it's negative. If I'm pushing it that way or pulling it that way, it's positive, okay? All right. Now, what about net torque? Well, it's just the sum. Anytime you see net, it's just the sum, or you can write it that way, Greek letter tau. The sum, or the sigma, capital letter sigma, or you can say just net. Either way, the sum of all your torques, okay? Now, notice the direction here of all these different torques. Boy, we got a bunch of different directions, don't we? We've got one that's going positive, one that's going negative, one that's going negative, another one that's going positive, and this one would be positive, okay? So holy smokes. Well, again, we just need to know the amount of force, we need to know the radius, and then the angle at which it's applied. Well, this one here is at a 90 degree. Let's see. That one's at a 0 degree. So that one's 0. And then this one, okay? That one's almost 90, but not hardly, so we'd have to use sine there, and we'd have to use sine there. Okay, but you just add them up. Which third force on the wheel applied at point P will make the net torque 0? Okay, all right, now notice that this is going counterclockwise. See, it's pulling it, making it rotate that way, so that's positive torque, okay? Well, we want to make the net torque 0, okay? It cancels the torque, okay? So we're pulling it, it's actually going to do what? If you pull it here, it's going to do what? It's going to go clockwise. So the net torque, now I didn't say there wasn't torque. We're looking at the net torque equaling 0, okay? See, there's torque here and torque there. You add them up, it equals 0. All right, gravitational torque and what? And the center of gravity, okay. All right, so when we know that gravity always pulls towards the center of the earth, and based on the size and shape of the object, the mass of the object will determine its center of gravity. All right, now notice right here we use that little symbol there. It looks kind of like a target on a bullseye, but it's really not. That's what it makes me think of when I see it, but I guess because of the black and white. But anyway, that's what I've always thought of it when I see it. But that point is called the center of gravity, okay? The center of gravity, again. So again, that's where the net force of gravity acts at a single point, okay? A single point. Now, let's do an example here. You got a 3.2 kilogram flagpole, extends from a wall at an angle of 25 degrees. Its center of gravity is 1.6 meters from the point where the pole is attached, okay? All right, now, to the wall, what is the gravitational torque on the flagpole about the point of attachment, okay? All right, so you got your radius, you got your moment arm, and here, your line of action. Well, how do we find that? Well, all right, well, that's how we find it. We substitute in to find torque, and notice now that the torque here is negative, okay? All right, and why is it negative? Because notice that it's moving. Gravity is pulling it what? It's pulling it clockwise, okay? So you take your radius times the mass times gravity, and you get a negative 45 newtons. And y'all, that's why it's negative, okay? Because notice, even though you're raising it up, you got to realize something. Notice it's talking about gravitational torque. Gravity's pulling it clockwise, okay? So you got to watch that, okay? All right, so an object that's free to rotate about a pivot will come to rest with the center of gravity below the pivot point. Well, okay, no duh, right? If you've ever played with rulers, I know when I was in school, sometimes we'd take our rulers and had a little hole in the end of it, and we'd hold it and swing it back and forth, or pick it up and drop it and watch it stop, because we were bored, killing time. Teachers would get aggravated at us, and say, quit doing that, you're distracting other students. It's still working. So anyway, that's how this works. So notice that when the center of gravity is below the pivot point, the weight, of course, is 0, and there's no torque, okay? All right. All right, which would be the center of gravity? All right, now think about it. Well, of course, it'd have to be A, center of gravity. It's in the center of the two. All right, now, okay? All right, the torque due to gravity when the pivot is at the center of gravity is 0. Well, I would think so, y'all. That's called balance, okay? That's saying that it's in equilibrium, okay? All right, that makes sense, does it not? Like if you've ever taken something and balanced it on your finger or balanced it on something, well, okay, the center of gravity is here, okay, CG, and so guess what? There's no torque. because it's at the center of gravity is at the pivot point, okay? All right, looking here, we're going to calculate this, the center of gravity. We calculate the torque on either side of the pivot, which is located at the position XCG. That's called the center of gravity. Oh, by the way, too, notice how the center of gravity is much closer to the larger mass than the smaller mass. Well, again, why? Because that is the point at which it will balance. If you've ever handled swords, you know, a really good sword will have the center of gravity up very close to the handle, okay? Why? Because it makes it much easier to swing, okay? You don't want it heavy out on the end of the blade. You don't want a lot of metal on the end of the blade, okay? Because then what? Well, it's going to be really hard to swing. You're going to have to really work to swing it. But if the pivot point is close to the center of gravity, okay, real close to the center of gravity, then it's going to make it really easy to pivot, okay? And if you've ever noticed that, I think about Pirates of the Caribbean when Will demonstrates to Norrington how well he manufactured this sword, okay, the balance, it balances close to the handle, okay? All right. Yeah, you don't want it heavy on the end. If anybody watches Forged in Fire, you know, they'll talk about that. Well, they're talking about the center of gravity. Okay, so how do we find then the torque, net torque? Well, again, the torque of 1, all right, where are we at now? 1, all right, notice that 1 is pulling downward, okay, and 2 is pulling downward also, okay, but 1 is going to go clockwise and 1 is going to go, let's see, counterclockwise, right? Okay, let's see, this will cause a counterclockwise motion, that would cause a clockwise motion, right? Okay, but since this one is more massive and the pivot point is close to the center of gravity or on the center of gravity, which way is this thing going to rotate? Well, hopefully, if it's balanced, it's not going to do either, okay? All right, so the total net torque then is equal to what? How do we find, well, excuse me, the net torque there has to be 0. Now look, and again, what I just said, you hope that it's at the pivot point, because if it is, then you have it balanced, and guess what? There's no torque. There's no net torque. What I got to be careful. Sure, there's torque here, and there's torque here, absolutely. But there's no net torque because it is balanced, okay? They cancel each other out. Now, so that being said, we substitute in for our equations the distance, which is the radius times the force, mass, and notice it's the change in distance now, okay? Then we come up with this equation right here. Now, you know that that is in meters. The location of center of mass is XCG, and of course that is going to be in meters, okay? So please add this equation to your formula card, all right? Okay? Please add this to your formula card. That is how you find the center of gravity of an object, okay? All right. Okay. All right, so since it does depend on the distance from the mass, the center of gravity does, then objects with large masses, of course, as I said earlier, will count more heavily. That is why it tends to be closer to heavier objects. I've already said that. Now, again, what if I had several different objects? Well, look, y'all, the center of gravity in the x direction, notice you just add them up. The distance times the mass, the distance times the mass, the distance times the mass. If you had 4, 5, 6, just keep adding them up, and then divide by all the total masses. Okay. Same thing in the y direction, y'all. What if it was in the y direction, like that, and we wanted to know the center of gravity? Okay, same thing. Same thing, okay? All right, notice they tell you what exercises, too, it is. Okay? So just, write those equations down on your formula card. X direction, center of gravity, and really it's the same thing. You just change the y. That's all you got to do, okay? All right. What about rotational dynamics? All right. Let's go ahead. We've talked about angular acceleration. Now, we've talked about angular speed and angular acceleration. Now let's look at angular acceleration when it applies to torque. Well, we know that tangential acceleration, okay, is a force divided by the mass. Okay. Well, what about angular acceleration? Well, we just substitute what? We substitute the mass times the radius. And of course that will give it in what? That'll give it to us in radians, or excuse me, the angular acceleration yeah, that would be newtons, that would be meters per squared, yeah. Meters per second squared, yeah. Okay, so compare torque to angular acceleration. Notice that the relationship, if we take torque and we substitute for force and we want to find the acceleration, because what is this right here? That's actually MA, isn't it? Yeah, sure is. All right, so to find the angular acceleration, it is the torque divided by the mass times the radius squared, okay? So again, here you need to write down another equation. That is angular acceleration using torque. Okay. All right, now, so Newton's second law, and of course rotational motion, does apply. Just like it does in a linear fashion, the same applies for an angular fashion. Now notice, because the objects rotate together, each particle has the same angular acceleration. Okay? All right, because they are moving together. Okay? So the torque for each particle would be what? Well, we use that previous equation and add up net torque and look at what we get. So the net torque is what? Well, the same as it was linear speaking. What about rotationally speaking? Well, right there. Okay. Or in other words, it's what? It is the sum of all the mass times the radius squared times the rotational or angular acceleration. Okay? Okay. So there's you another equation right here. Okay, to find net torque. And of course that is Newton meters. The units are still Newton meters. Torque is torque. Okay. Now, what about what we call the moment of inertia? Well, moment of inertia is proportionally constant between the angular acceleration and net torque. Okay. So to find the moment of inertia, in other words, how much mass or how much torque does it require to move a particular object? Well, the moment of inertia is how we can determine that. And notice our units here. The units for the moment of inertia are kilograms meters per second. So if we need to find out how much is required to cause an object to move, or which one will be easier to move than the other, we look at it here. And notice too, if that radius is small, then the moment of inertia is small. If the radius is high, it's high. Same thing with mass, okay? Now, so Newton's second law for rotation can be simply written this way: the net torque divided by the moment of inertia. And the net torque causes angular acceleration. Okay? All right. If there's no net torque, if that is 0, then there's no angular acceleration. Okay? So, moment of inertia around a around a body of the moment of inertia is the rotational equivalent of mass. So look, which is going to be easier to move, this situation or this situation? Well, the mass is concentrated around the rim on this one, Here, it's concentrated around the center. So it's going to be a whole lot easier to move this one. Okay? You don't need as great a moment to get things to moving. Okay? All right. All right. Again, now let's look at linear dynamics and linear dynamics and rotational dynamics. Notice the comparisons here. Force net, newtons, relates to torque in that the units are Newton meters, and you say, well, why do we use Newton meters? Again, that is the force applied over a what we call a lever arm. Okay. All right. Now, moment of inertia. Well, that has to do with the mass and the distance the mass is located from the radius. Angular acceleration, very similar. Again. Okay. And even acceleration and angular acceleration, the relationships there. If you have a net force with linear motion, you have acceleration. If you have a net torque, you're going to have acceleration. All right. Now, very important slide here. You say, well, now when we're calculating moment of inertia, not everything has the same dimensions. You're exactly right. This all depends on two things: the shape of the material, and most importantly, where is the point of rotation? Okay. All right. Notice, if the point of rotation, a thin rod, notice it says rod with any cross section about a center. Okay. So where is our point of rotation going to be? Okay. Where is it? All right. If it's here on this rod, notice the equation you have to use would be I is equal to 1/12 over the total mass times the length squared. All right. If it's on the end of the rod, that's where the point of rotation is. That's your moment of inertia equation. What if it's over a slab and it's going through the center of the slab? Very similar to the rod, isn't it? Okay. What about on the edge? And by the way, notice it's the square of A side, not B side. Again, notice it's all dependent on the point of rotation, moment of inertia. Okay. Notice right here, same thing. What about a cylinder or disc? 1/2. What about a cylindrical hoop? Just mr squared. What about a solid sphere? What about the spherical shell about a diameter? Same thing. Okay. So, are you going to need to remember all these? Well, it wouldn't hurt, okay? If you want to make you a little drawing on your formula card and do that, that would be fine, okay? All right, and put those equations on there. Okay, so using Newton's second law to cause or produce rotation, well, again, y'all, we can find the torque net if we know the moment of inertia times the angular acceleration, and or we can find the angular acceleration using torque divided by the moment of inertia. Okay, so what does that lead us to? All right, if we want to find the actual velocity of an object turning, now again, we're not talking about angular velocity, we're talking about the velocity of the object. Okay, all right, in other words, how fast is it moving right here? Because look, that's all we care about. All right, see right here, that's all we care about, is that right there. We don't care about what's going on in here. Okay, well, why? Well, because where's your rope and the mass? See, it's on the outside, isn't it? And notice it's either moving up or down. So in a sense, it's in a linear fashion, even though it's being produced about a rotational axis. Okay? And you say, well, why can't we use the linear equations? Well, because it's not on a flat, it's not on a flat surface. It's moving about a rotational axis, okay, or an object rotating about an axis. So the velocity of the object is simply put, we've actually already been over this, the angular velocity times r, and that will be radians. Well, actually, yeah, it'll be, is that radians per second? Yeah, radians per second. But we want to find it, though, in, oh, shoot, I can't believe I just did that. I'm stupid. All right, that is radians per second, and this is in meters, so it'll be meters per second. There we go. Same thing here. If we want to find its acceleration, meters per second squared. That is in radians per second squared times meters, and you get meters per second squared. Okay. So it's similar to linear rotation, except it's not moving across a surface like this. It's not moving in a linear translational fashion. It's moving around, see? See, if I keep pulling, if I pull this rope in the opposite direction, what's that thing going to do? It's eventually going to come over here and go back this way, isn't it? Okay? Okay. All right, I hope that helps.